Hello, my name is Jonathan Walker. I'm from Panama City, Florida, and my project is on the development and implementation of a bio-based filter to mitigate the diffusion of harmful pollutants from internal combustion engines and combustion processes. So getting into the problem, internal combustion engines and general combustion processes use fossil fuels, and as a waste product, they produce pollution. America has a huge dependency on fossil fuels, demonstrated by the fact that it generated over 60% of the electricity in the US last year. They're used very commonly, especially in the transportation industry, due to internal combustion engines being used in cars and trucks. The effects of this are that cars can cause anywhere from 50 to 90% of air pollution in suburbs, demonstrated by the fact that the average passenger vehicle generates 4.6 metric tons of carbon dioxide a year on average. The emissions are harmful to us through climate change, which has already caused a ton of disruption, as well as land damage such as acid rain, harming ecosystems, and ocean acidification. The processes to actually harvest the fossil fuels also cause land damage. Finally, they harm us humans due to some of them being carcinogens, so they have the possibility of causing cancer, as well as irritating our respiratory system and mucous membrane. Not only this, they can also reduce visibility whenever smog is present. The existing methods for mitigating the amount of pollution include carbon capture at factories as well as open air carbon captures, but these both have their own shortcomings. Carbon capture factories are stationary, so if the pollution producer is mobile, it can't be followed, as well as it's very expensive to carry out the very energy exhaustive process of actually capturing the carbon. Open air carbon capture is too expensive for mass scaling and it's inefficient due to the low concentration of the carbon-based emissions once diffused into the atmosphere. An ideal solution would be economical, portable, and effective. From this, I devised my solution, which included pollution control at the point source of the emission so it's more concentrated, as well as adding on to existing devices so that it's more economical, and there's no need to build an entirely new infrastructure device to be able to purify its own emissions. Finally, I thought that there should be a process that can be scaled to any volume of emissions, and the byproducts that are produced from the process to either be non-harmful or beneficial. From this, I came up with my engineering goals for this project, which were to create a filter that appends to the tailpipe of a car, as well as decreasing the volume of harmful pollutants, and any byproduct that's made as the process is beneficial to humans and the environment. I also wanted to use physical, chemical, and biological based processes to purify the emissions, and from these different methods have some form of redundancy built in, as well as making it extremely economical to where it costs less than $50 to produce a model. Once my engineering goals were in place, it was time to start the development process. First, I started with the whiteboard and ideated the technology that I would use to purify the emissions, and I came up with dissolution, absorption, and mechanical filtration, among other things. From that, I made a 2D blueprint for the full filter with the respective technologies in their respective locations. And once I had that, I made a 3D CAD model of the filter components that I needed custom made, and I 3D printed them. Then I used traditional construction methods to fabricate the other parts of the filter that I needed, and from there, as you can see in figure 6 on the bottom left, I assembled the filter, and this included part integration and making sure everything fits snugly and airtight so that if there were any emissions that went through the filter, there wouldn't be any leakage. Getting into the specific functionality of the filter, as you can see on the left, I have a diagram. Part A is the modes to mitigation module, and it's focused on mitigating heat, carbon dioxide, carbon monoxide, nitrogen oxides, particulate matter, and hydrocarbons. And it uses processes such as heat dissipation through heat sinks, adsorption, dissolution, and mechanical filtration to do so. Part B is the dissolution tube, and it ensures that any nitrogen oxides or sulfur dioxide that was dissolved by the water vapor condenses and it's fed into the APC as a nutrient solution. Whenever they're dissolved, it forms nitrous acid as well as sulfurous acid, and these can be used by algae. Part C is the algal protection complex, which is the module designed solely to keep the algae alive. It contains a conduit to receive the nutrient solution from the dissolution tube, LED lights so that it can perform photosynthesis, and heat sinks so that the algae doesn't become too hot. On the right, there are the mode to mitigation module or rings with chemicals that perform the processes of purification, as well as the water reservoir that heats up to form water vapor. And in the lower right, there's a view of the algae and the algal protection complex, and it's backlit by LED lights. The algae plays a role in filtration by taking in the carbon dioxide, using it for photosynthesis, and releasing oxygen, which is helpful for humans and the environment. To test the filter, I used a 5-gas emissions tester, which measures oxygen, carbon dioxide, nitrogen oxides, carbon monoxide, and hydrocarbons, and I used a 2006 Jeep Wrangler as the source of the emissions. In order to observe the effect of the apparatus on the emissions, I ran an emissions test with no filter as a control, and then I attached the filter and ran another emissions test to see any differences. I ran 54 trials at 600 RPM, which is idle, and 54 at 1500 RPM, which simulates urban driving. In the bottom left, there's the filter connected to the car during testing, and on the right is the interface that I use in order to obtain the emissions test results. These are the results of the 600 RPM trials, and with the filter in use, there was a decreased amount of carbon monoxide, carbon dioxide, and nitrogen oxides, but an increased amount of hydrocarbons, which was unwanted, and an increased amount of oxygen, which was very exciting. The t-test yielded a p-value of under the confidence interval of 1,000 for all of the trials, meaning that the filter's effect was statistically significant, and Cohen's d further signifies this. These are the results of the 1500 RPM trials. Once again, there was a decreased amount of carbon monoxide, carbon dioxide, and nitrogen oxides with the filter in effect, but there was an increased amount of hydrocarbons again, which was undesired, and an increased amount of oxygen, which was once again very exciting. All of the p-values for the t-test were once again under the confidence interval of 1,000th, with the exception of the hydrocarbons trials in the bottom left, but it was under the confidence interval of 0.05 with a coherence d of 0.607, signifying that there was an effect that the filter had on the emissions. These are the data tables for both of my trial sets at 600 RPM and 1500 RPM, and the most exciting thing for me to see in these data tables are the percent changes that are occurring with the apparatus in effect. For instance, there was a decrease of almost 80% in carbon dioxide at the 1500 RPM data table, and there was an increase in oxygen on the scale of nearly 2,500% at the 600 RPM data table. Seeing these monumental changes gives me a lot of hope and a lot of excitement about this project. The trial data that I obtained was mainly desired. The only thing I was dissatisfied with was the hydrocarbons increasing with the apparatus in effect both times. I think this is due to the inner tube, as it heated up and released hydrocarbons of its own since it was made of rubber, so I need to change that material that provides a link between the tailpipe and the filter. Heat mitigation was super tough for sustained periods of time since I used a passive cooling system within heat sinks. If I used an active one that's more aggressive, I think it would serve me a lot better. And the water nutrient conduit worked amazingly, which I knew is a very big step in the path to getting the algae to be self-sustainable. And so the newest questions I have after that testing is, what's the longevity of the filter components because it's not a reversible process? How would specialized components specifically made for the filter alter its performance? I think that it would improve a lot just because custom made means that it can be optimized to its task. And how would it perform with other carbon-based combustion processes such as diesel engines? Based on a couple of assumptions and stoichiometric calculations, I was able to come up with these numbers as a comparison between the volume of emissions between the car alone and with the filter in place. If you'd like to know about the process that I came up with to get these numbers, please ask me and I would love to tell you about it. In conclusion, my project was a success. All of my engineering goals were met except for reducing the amount of hydrocarbons, but using different materials should get rid of this issue. There was an increase in the amount of oxygen, and this reminds me of a tree, which makes me very excited for the future of this project. Moving forward, I'm going to be refining my prototype and improving it, as well as adding more filtration methods like spider plants due to their ability to filter out toxic gases, as well as testing filtration processes on other types of combustion processes like diesel, and ensuring the sustainability of the algae through it all so that it can live indefinitely and keep filtering. There's a ton of applications to this project, such as attaching it to the car's tailpipes to reduce the amount of harmful pollutants emitted, and this will bridge the gap until electric vehicles become more prominent and available to everybody, while still having that same effect. There's also an overall reduction in carbon footprint through its use, so it's more economical and it's widely available so anybody can use it, as well as allowing fossil fuels to be greener, and there's cleaner energy productions for those industrial and energy generation processes. This can also be used for improving the environment and the air quality for vulnerable people and animals alike, especially in these times. This concludes my presentation. If you have any questions or want to discuss anything, please let me know or ask me, and I would love to talk to you about it. Thank you for listening and have a great day.